So yeah, my name is Yury, and today we're going to talk about async I/O and what can happen to it in Python 3.8. So a lot of this information was just announced. I'm a Python core developer for the past 5 years, and I was lucky enough to work on async await syntax, asynchronous generators, comprehensions, and lately context variables. I'm async I/O maintainer, and I also co-founded HDB. An important thing to note is that I will host an open space about async I/O and HDB, so feel free to join me after the talk. You can follow me on Twitter and GitHub. My nickname there is 1st1. So before we talk about async I/O, let's talk about async await a little bit. And the recurring question that I hear about async await is why do we even have it in Python? Why didn't we just remove the GIL, or why didn't we just merge G-event to standard library or stackless Python? And to answer that question, I'd like to tell a story, a little story about a pull request. So a pull request was submitted to async I/O about a month ago to add names to asynchronous tasks in async I/O. Just like threads in Python have a name, why don't we have a name for asynchronous tasks? That simplifies debugging sometimes. And the first change in that pull request kind of got my attention. So the change is about creating a reference to an itertools counter object. And my initial reaction was, why do we need this? We basically can have just an integer, and we can have plus equals 1. And my colleague Elvis and later I said, well, we don't need this stuff, just have a global variable, an integer variable. To which the person replied, well, I'm actually using this approach because it's used in threading module in Python, and that's a thread safe approach, how you do it. To which I a little bit arrogantly replied that, well, in Python we have a GIL, it protects execution of all opcodes, so plus equals 1 is a thread-safe operation. To which that person replied, what output does this script give you then? And I'm like, oh my God, there is a script. So the script is actually pretty simple. It launches 30 threads, and every thread just executes a for loop and modifies some global variable. But 2 lines got my attention at the end of the script. It's expected counter value and actual, so I kind of knew what will happen once I run the script. And I already knew the explanation, but I opened the disassembly just to show you guys what actually happens. And indeed, plus equals 1 is a GIL-protected operation in Python. It is thread safe. But plus equals 1 in Python compiles to 4 different opcodes. And those can actually be racing with each other, even with the GIL. So the point of this story is that I have a lot of experience actually writing multi-threaded applications, and I know how Python runtime works, I know how Python compiler and C eval loop work, but still I made this mistake unconsciously. So threads are actually pretty hard to program correctly. So why do we have async await in Python? Well, obviously to handle that 10 to the power of 100 connections on your Mac Mini. But the other reason, and the core reason why we actually have async await, why we have it in C#, why we will soon have it in Rust, is because it makes concurrency visible. So you actually know when you're about to give up control in your own code. Also, data structures are not racy. So if you are using some data structure in async await code, you don't have to worry if it's thread safe or not, unless this data structure is asynchronous. And there is a general rule of thumb. If you see a library that uses async await, it's probably meant to be used with async await. This is something that you cannot really say about a regular blocking IO library in Python. If you just look at some driver for some database, you have no idea if it's actually thread safe, if it doesn't have some global cache or something like that, and just blow up in production when you start to use it. So let's get back to async I/O. And about a month ago, we released Python 3.7, and the headline feature for async I/O, I think it's context variables, and we'll talk about context variables a bit later. We also changed async I/O, upgraded async I/O own code to use async await. So if you want to look at some implementation details or how some things work. You will now see some clean async await code, and you won't see those strange and weird yield from expressions and generators. We now have async run function, and this is something, I guess, where credit goes to Curio. As soon as I saw Curio and the Curio run function, I wanted to have it in async, but unfortunately we missed the window in Python release schedule, so we had to wait until Python 3.7 to finally have this function. There are a lot of other async IO APIs that we added in Python 3.7, and every API in this list basically deserves at least a lightning talk. Just to highlight some of them, there is new high-level API to use the sendfile system call. You can send file over individual sockets, or you can use a high-level sendfile method to send file over transports in async IO. You can upgrade non-encrypted transports to TLS dynamically. There is a high-level function async IO create task. This is something that was clearly possible to do before. Before you just could call an event loop method to create a task, or you could call a special high-level function which is called ensure future, quite a cryptic name, but it actually did create a task for you. But now we have this neat little function that does that for you. Another low-level function is get running loop. We'll also talk about it a little bit later, and a new buffered protocol API that basically allows you to implement low-level async protocols and tightly control how you are actually using your receive buffer to minimize the number of copies. Also, during Python 3.7 development lifecycle, another implementation of async IO event loop appeared. It's called Tokyo, and it's implemented in Rust. And the idea is that in Tokyo, they have their own implementation of asynchronous task, and we just discovered that async IO tasks aren't actually easy to implement in third-party code. There are some APIs that were just clearly missing. So now we've added those APIs, and async IO is complete on that front. So when people talk about async IO or use async IO, they always complain that async IO is super hard to use, and they are actually right. And in part, the async IO documentation is at fault here. It's super complex right now. It's relatively unstructured, and the accent that it makes on different APIs, they just aren't right. So actually, async IO basically consists of two levels. One is a high-level normal layer with functions like async IO gather or create task or sleep or streams API. And then there is a hardcore layer, which is basically anything that touches the event loop or protocols or transport or async IO futures. And the rule of thumb is that you don't really need to know or use those low-level APIs ever, unless you're writing a library or a framework for async IO. For your day-to-day usage of async IO, you basically just need to know 7, maybe 10 async IO APIs, and that's it. You can write any async IO applications with that. So let's talk about async IO run. And what you see on the screen is a typical way of how you would launch an async IO program prior to Python 3.7. So you would need to call the get event loop function, which is a weird function actually. It could return you a new event loop, or it could create you it could return you an existing event loop, or it could actually raise you an error, or based on what kind of event loop policy you are using, it could do something else. Then you would run a run until complete method, which basically just runs a coroutine until it's complete. And then you would close an event loop, or at least you would think so. The problem with this code isn't that just that it's verbose, it's also slightly incorrect. The problem is that closing event loop is usually not enough. You also need to cancel all asynchronous tasks that are still pending. You need to correctly close all asynchronous generators that exist. So in Python 3.7, we now have this new function, which is called async IO run. And this is basically an equivalent code, but it does all those correct things to do when you close the event loop. And this is actually a trimmed down implementation of async IO run. And if you can see, it's pretty complex, actually. You need to understand a lot of low-level details about async IO to write this function. So just use it. Ideally, starting with Python 3.7, your application should consist of one single coroutine that's an entry point. You can call it main. You initialize your application in that coroutine and then just use async run. And ideally, you should just use async await for everything. You shouldn't even try to use low-level APIs or access async event loop. One of the things we had to solve when we were working on adding async run is to what should we actually do about the loop run forever method? And the method is actually pretty simple. It does literally what it says. It just runs the loop until the program terminates or until you explicitly stop the loop. So the common pattern, and this is actually an example from the asyncio documentation. The common pattern was to get an event loop, create a server, run the event loop forever, then maybe handle keyboard interrupt or system exit exception, and then you kind of try to close the server, you try to wait for it to close, and you try to close the event loop. And we already know that it's not a perfectly correct code. So in Python 3.7, we actually addressed this problem by making servers asynchronous context managers, and we have this new method, new coroutine method on async servers, which is called serve forever. So this is an equivalent code, but again, more correct than the previous one. As you can see, it's like 2 times shorter, and it's easier to use and reason about. And lastly, I want to focus our attention on getRunningLoop functions. So there are 2 reasons why you might want to access the event loop. Either you are interacting or writing some low-level code that requires you to pass the event loop reference to it. Or you're using some API in asyncio that we don't have a high-level async await equivalent for. So starting with Python 3.7, we now have this function, getRunningLoop. It's super simple. It's super deterministic. It fails if you call it from anything else but from a callback or a coroutine. It doesn't work with asyncio policies or anything like that. It just returns you the currently running event loop. And you can use those low-level APIs like add-signal-handler, which is relatively low-level, and for Python 3.8, we'll probably have a high-level async await version of this API. But for now, you have to do it this way. A couple of don'ts. Don't use the coroutine decorator. Don't use generator-based coroutines anymore. We'll probably deprecate them in Python 3.8 or 3.9 and just remove them completely in Python 4.0. And also, again, don't use low-level event loop APIs pretty much ever. You probably don't need them unless you're writing some protocol implementation or, I don't know, custom thread pool or something like that. Now let's talk about async await code. So what async await code is actually good? Pretty much any code. What code is good? The one that you can write quickly or maybe maintainable or beautiful or robust or fast. Usually it's a combination of those metrics, but the problem is that the 3 of these are subjective. Some of them are highly subjective. And in reality, you can actually only measure the last 2. And the way you measure them, you monitor in production your code. You see how it performs under load. And the question now is it even possible to monitor an async IO application? What can you do about it? And to answer this question, we need to look at how async IO itself sees your code. What does it think about your code? So async IO doesn't really know what it's doing. It has a queue of callbacks. It executes it, does some IO, executes more callbacks from the queue, and this process is repeated. So basically, it's just an endless sea of callbacks for async IO. There is some structure that you, as application author, probably know, but you have to either maintain it explicitly or you don't have it at all. It's just callbacks. So this is something where context variables can help us. This is a new module in Python 3.7. It was proposed initially in PyBay 550. It had 4 different revisions, and then we simplified the whole thing. And PyBay 567 is something that actually details the latest version of context vars module. There was about 900 emails on Python ideas and Python dev. It was super hard to actually push this thing through. But finally, in Python 3.7, we have context variables. First of all, warning, it's magic. And like any magic, you shouldn't just use it because it's there. Sometimes you actually want just to pass something via a variable or an argument to a function. But in some cases, it's pretty much necessary to use context variables. So it ships with Python 3.7. It's part of standard library. Async.io supports context variables out of the box. You don't need to do anything about them. And actually, the decimal module uses context variables now in Python 3.7. So prior to Python 3.7, if you used decimal module and you had different decimal context and different coroutines, then your computation probably had bugs in it. Now decimal context uses context variables, so async await code works correctly with decimal module. And actually, NumPy library will use context variables, or maybe is already using them pretty soon. So context variables, again, this is a standard library module, so it's not a syntax extension. So to create or to interact with context variables, you first need to import the module, and then you have to declare your context variable programmatically, basically by calling some API function and giving your variable a name. To assign a value to a context variable, you use the set method on that variable, and to read the current value for a context variable, you use the get method. So if you get back to our example of how async.io sees your program, and let's say that we are working on a web server, web application, and we have this task ID context variable, and we assign some randomly generated unique number to that variable for every request that your application handles. Then suddenly you have the structure. Every callback automatically knows where it is coming from what request it is coming from. So how can you actually use context variables? You can use them for monitoring, obviously. You can store a timer in your context variable, and you can increment the timer or do some operations on it. You can use it for localization. You can memorize what kind of current language the currently served user has, and you can access that information pretty much anywhere, like even in JSON serialization library if you want. You can do the same for security. You can use it for debugging. You can have a context variable, put something into it, and check it in some different part of your code, and if it reads the same value, then basically those two things are connected in your application. And obviously you can use it for execution context, again, for stuff like decimal context or NumPy error context. You can use context variable to store this context-related information. Now, we have context variables in Python 3.7. Life is beautiful, so maybe that's it. Maybe async.io is good enough. Unfortunately, not really. We still have a long road ahead of us. We still have a lot of improvements that we want to do in async.io. And before we talk about them, we probably need to talk about Trio. So Trio is a new framework, a new async await library, pretty much incompatible with async.io, and that's by design. It's created by Nathaniel Smith. And the important thing about Trio is that Nathaniel actually designed it from scratch. He, unlike async.io that was designed and took some design decisions from Twisted and from Tornado. And that's how, by the way, async await syntax was born. Nathaniel observed how people use async await, how they use async await with libraries like Curio. And he decided that, well, we can actually improve some things. We can actually do them differently. So Trio has a hard focus on usability and on doing things in just one way, basically following the Python Zen. And in my opinion, Trio got many different things right. So the last bullet point here is a link to a YouTube video. That's a Nathaniel talk at PyCon US this year, and I highly encourage you to watch that talk. It's pretty good. And in fact, I actually borrowed a couple of slides from his talk. So if you go back to 1958, this is how a typical program looked like. And what you see, you don't need to read the code, but the idea here is that every line has a number, and some lines have basically jumps to other lines like this. But what happens if we visualize all those jumps? We have a picture like this. It's completely untraceable. About 10 years later, Dijkstra posted his letter, which was titled "Go-to statement considered harmful," and he came up with this idea of structured programming. And the idea is that he proposed to break down the program into a series of blocks. So we have an if block, we have a loop block, we have a function call. And what all those things have in common is that they have only one point how you enter the block, and you have only one point how you exit the block. So basically, whatever program you have, it can be decomposed into those structures, and you can trace the program. You don't need Go-to to create programs. And if we think about async I/O and asynchronous programming, we have a lot of go-tos there. We have those callbacks, and those callbacks execute in some random order. And sometimes it actually influences how you write your high-level async await code. Because in async I/O, you have this async I/O create task function, which creates an asynchronous task that runs in parallel with your code. You have no control over that. If an exception happens there, well, it will be logged, but good luck catching it with the try except statement. So in Trio, there is only one way how you can spawn an asynchronous task. And you do that through an object called nursery. So you open a nursery context. Nurseries require you to use asynchronous with statements. And inside that block, you can actually spawn asynchronous tasks. But there is a guarantee that if one task crashes with an exception, then all other tasks will be canceled automatically. If your current parent task gets canceled, then all those tasks will be canceled as well. So you have a hard guarantee that you can only you enter the nursery one way, and you always exit it, and you know that when you exit the nursery, all resources will be completely cleaned up. And despite the funny name, because, well, tasks get born in nursery and they always die in nursery, there is no way of graduating from nursery, the idea is actually pretty good. The control flow is always traceable. There is almost no out-of-order execution whatsoever. Exceptions are never lost, and you can actually put your with block around the nursery or try except block around nursery, and it will just work. So basically, they solve this go-to problem in concurrency. So if we get back to async I/O, and again, we have this problem of lots and lots of callbacks barely linked with each other. And we think about a typical async I/O library. Usually, let's think about some HTTP library. Probably it has some high-level HTTP client object, and that HTTP client probably schedules some callbacks, and those callbacks schedule more callbacks. Probably it has a transport attached to it, and maybe a protocol. But the real question is, what happens when an exception occurs somewhere in some callback? And there is no clear answer to that. It all depends. Ideally, you should create your callbacks for async for low-level async protocols and drivers. In this way, you should have a try-except block in it. And if something happens, you have to propagate this exception somehow to clean up resources. But unfortunately, most libraries just don't do that. They assume that there are no exceptions and the code is perfect. Usually, most common paths are somewhat protected, but you always have to come up with this ad hoc mechanism, how you handle those exceptions, what you do about them. And this is basically like a big bug magnet in async I/O. A lot of things sometimes break and go unnoticed. So what do we actually want async I/O to do for us here if an exception occurs? We want async I/O to automatically clean up all those resources, to close your callbacks, to close your connections, to correctly propagate the exception. And I have an idea for Python 3.8, and again, this is just an idea. We might have it in 3.8, maybe we'll change the name or we will change the API. But the idea is to add this new low-level method to event loop and call it create supervisor. And again, this is for low-level async I/O libraries. So create supervisor would return you a supervisor object, which basically will mirror all event loop APIs. So it's like a small copy of an event loop made just for you. Because we do it this way, this small async I/O event loop copy knows about all resources that you scheduled through it or allocated through it. So if something goes wrong, it can actually consistently clean up those resources just for you, just for your code. So a little taste how it might look like. So if we have, again, our hypothetical HTTP library, and we have this high-level get method. Inside that method, we get a reference to the currently running event loop. We create a supervisor. And inside that context, we can actually access all those low-level APIs. And there is a hard guarantee that if something happens within that async with block, then all those resources will be completely cleaned up. If you look at a lot of async IO libraries like async.pg or AIO-HTTP, you will see that a lot of code there, approximately 30% of the code, is built around handling those exceptions and callbacks, about propagating those exceptions, about handling timeouts and cancellation correctly. And it's super hard to do, it's super annoying to do, and it's super hard to test. So with supervisors, hopefully, it will be just easier to write such code. I also have another idea for Python 3.8, and while supervisors are for low-level async IO code, this is something for high-level async IO code, and that's basically a task group. The original idea was first implemented in Curio, so thank you, Curio. But the task group that I want in Python 3.8 is closer to Nathaniel's nurseries. So the idea is the same. You create a task group, you can spawn some asynchronous tasks inside that async with statement, and there is a hard guarantee. If something goes wrong, if one task crashes, then all other tasks will be canceled. If all of them, if the parent task is canceled, all of them will be canceled. So it gives you more control over how exactly you spawn your asynchronous jobs. So task groups probably will use the create supervisor API under the hood, and we have some idea about some ideas how to enforce correct usages of create supervisor. Like we can prohibit you to call get event loop in your low-level API, so that if you create supervisor, you have to pass it explicitly in all your low-level code, so that it will make the resource management even simpler for you. Task groups probably will be way more convenient API than async IO gatherer, which actually has a big problem. By default, async IO gatherer doesn't cancel asynchronous tasks if one of those tasks crashes. So if something goes wrong, async IO gatherer will just immediately propagate the exception. The crashed task will be, of course, paused, but all other tasks will just continue their execution, and you won't even notice anything. It is possible to use gather correctly. You have to pass this return exceptions argument to it, but the problem is that a lot of people don't know about that at all. So yeah, there is this limitation. And with task groups, you will be able to implement some nice patterns like batching tasks. If you have, let's say, 1 million things to do in async, it would be unwise to schedule 1 million tasks, because although tasks are lightweight, they still consume some resources. So they ideally should just batch those tasks in groups and create them in groups. So what else can we expect from Python 3.8 with regards to async IO? Well, first of all, we hear you. So when you complain on Hacker News or Reddit or Stack Overflow or Twitter, sometimes we hear those complaints and sometimes we try to address them. But ideally, what you should do, you should go to bugs.python.org, you should submit a pull request to GitHub, or maybe you should just send an email to Python Dev or Python Ideas suggesting your change or telling us about some bugs. So please do that. Documentation, the documentation for async has to be just rewritten from scratch, and this is something that I have been promising for a couple of years now, and I finally started to work on that. So hopefully in a month or so we'll have a new documentation for async IO with correct accents on correct high-level APIs, with high-level tutorial, with examples index, and all of that stuff. Likely we will have async IO create supervisor and async IO task group. Again, there is no hard guarantee, but all async IO maintainers actually want this functionality in one way or another. Maybe we will have a low-level tracing API for async IO, and this is what we originally created context variables for. Right now, it's impossible for you to tell what the event loop is actually doing. What are the latencies? How many bytes are flowing through some transport or through some protocol? And we have so many services like New Relic or Sentry, or maybe you're using Zipkin in your company. And what we want you to have a full visibility into what async IO is actually doing. And to do that, we need to design proper APIs so that you can use it for multiple different data providers. Maybe we'll implement proper timeout and cancel scopes, just like in Trio. And the idea here is that in Trio, when you are creating I don't know, an HTTP library or something, you don't care about timeouts. You don't handle them at all. There is only one mechanism in Trio how you set a timeout for some asynchronous code block, and you always use it, and it just magically works. So as I said before, in libraries like asyncpg and AIO HTTP, a lot of code is actually there just to implement timeouts and cancellation correctly. So if we find a smart way to adopt those ideas from Trio and async IO, we would simplify our lives a lot. Maybe we'll introduce new streams API. The problem with the current streams API in async IO is that for every stream, you have two different objects. You have a reader and you have a writer. And then you have a question, like if I want to close the connection, should I close the reader? Should I close the writer? Or maybe I should close both of them? So the API itself is very confusing. So hopefully we'll have a new version of this API in Python 3.8. Another idea is to have a context manager for the shield function. And shield function, not a lot of people know about it, but you use it when you want to create an asynchronous task that is impossible to cancel. A good idea where you would need a shield function is when you have a try finally block and you have some functionality in your finally block that must be executed regardless of what else is going on in your system. So this is how you use the shield function, but again, this is a function and it accepts a coroutine, so you have to factor out your code out of your finally block. So maybe we can actually design a context manager so that you just write async with shield and your code is shielded. We're also rewriting the SSL implementation basically from scratch for async IO. It will offer some stuff like SSL over SSL. It will offer better performance and more correctness, like when we are closing SSL transport, we need to close them correctly. Right now, async IO doesn't really do that. The good news here is that the prototype of that implementation will actually go to UV loop first, so we will battle test it, and then we put it into async IO. And lastly, maybe this is a personal pet peeve of mine. The canceled error is an exception in Python. So sometimes people put an innocently looking try except exception block in their asynchronous code just to log any kind of exception that happens in their code. What they do, they accidentally are blocking the canceled error exception, so they make the task uncancelable. They just break the cancellation flow of the entire asynchronous code that they are writing. So we probably need to make canceled error a base exception. And this is strictly speaking a backwards incompatible change, but the impact surface should be relatively small. So most likely we'll just do that in Python 3.8. This is it. Thank you very much. Any questions?
Any questions?
Do you plan on incorporating any good flowchart diagrams into your new docs?
These flowchart diagrams, or?
For different patterns.
What kind of patterns?
Just any of them, like the gather pattern.
Yeah, I think it might be a good idea to have at least some flowcharts in the documentation. Right now, we have a few super low-level flowcharts that I, for instance, don't understand. They were drawn by Victor Stinner, and they explain too much of an implementation detail about async IO. So adding flowcharts, I think, is a good idea, but we need to do it properly, because when you open a documentation page and it has like lots and lots of charts, you might be scared away and not really understand what is going on. But yeah, I guess we need to improve the documentation, and some flow charts can actually tell you a lot how different asynchronous tasks can be executed in parallel, and what to expect and what to guard against. So yeah, sure.
In terms of kind of using this in production, do you think that's a good thing? Should you use it, or is the API going to be kind of in flux between like 3.7, 3.8 in the future?
So we have this thing in Python. It's a relatively recent thing. When we add some APIs that we are not 100% sure about, we call them provisional. Like this buffered protocol that I mentioned in the beginning of my talk, it's a provisional API. And when an API is explicitly marked as provisional, in theory, we can even retract it. We can even remove it in further releases. We can change it in a backwards incompatible way. So some of those APIs will actually be marked as provisional if we add supervisors, because supervisors are super low level and invasive. Probably they will be marked as provisional. However, the chance of us actually removing them is pretty slim. For instance, asyncio, it's self-provisional for Python 3.4 and Python 3.5, and we never actually used that provisional status to make any backwards incompatible change or break asyncio in any way. So some of those things might be provisional, to answer your question, but it's still relatively safe to use them. If we are super unsure about some API, we just wouldn't add it at all.
Any other questions? Awesome. Thank you so much, Yury, for that great talk.
Thank you.